Coordinate systems are very important in finite elements. They're important from a theoretical standpoint, but also from the practical standpoint of data entry. There are many different coordinate systems that are used, and often in a single problem, a finite element user might call on 2 or 3 different coordinate systems. Our discussion here will start with some general terminology. Some of that is common in the different computer codes, and some of it is distinctive to certain codes. The two-dimensional theory is probably the most important for us to learn and to give illustrations. I'll only mention the three-dimensional theory briefly because it's much more difficult. We'll have a problem session at the end that will help us see some simple problems in 2D. Let's discuss some of the motivation for creating and using different sets of coordinates. First of all, commercial finite element codes have a default coordinate system built in that's usually a right-handed Cartesian system. And this is available to the user so that if you develop data for the grid points and so on, that they'll be referred to that default system unless you say differently. Now, different reasons for wanting coordinate systems involve these bullets shown below. You certainly have to enter a lot of geometric data, primarily that for the location of the nodes. You want to interpret boundary conditions in the most convenient coordinate systems possible. You need to develop material properties, and there are probably preferred directions for the materials, so-called principal material directions. You'd like to exploit various interesting geometrical axes and planes, for instance, axes of symmetry, reflective planes, and so on. The generation of elements itself often is helped by element coordinate systems. Now, that's often transparent to the user because many times the code developers will use a special element coordinate system for each of their types of elements. Then there might be an optimum system of coordinates in which to actually perform the solution, which for us is Gauss elimination. And lastly, when you read data out, when there's information to be brought out of the code, you may want to refer it to certain axes and at certain angled inclinations. Let me sketch some examples of coordinate systems. 2 of these are used a lot, and then the other 2 are more rarely used by the user. The first one is the rectangular system, widely used, often the default. And then the second is a cylindrical system that often is used by people where there are bored holes that have cylindrical surfaces to characterize. The spherical system shown below is not used very much. In fact, I've never used it, although I'm doing some balloon problems and I've come close to wanting a spherical system at times, but often people will settle with cylindrical. The fourth kind, curvilinear, however, is used a lot by code developers in developing isoperimetric elements, but that's transparent to the user, and a user would never create a curvilinear coordinate system because it's just too specialized. Often the origin is at the volumetric center of a given body, and then these curved lines extending in space. This is still an orthogonal system, as the others are, and those are so called because if you look at the displacements at the point in question, you'll find that regardless of which system you use, the local little increments of displacement are going to be perpendicular to each other. And so these coordinates can play both the role of establishing where a point is, and then secondly, to establish the small motions of that point in its own neighborhood. I'm going to define three major categories of coordinate systems. We're going to have nodal coordinates, then we're going to have element coordinates, and material coordinates. Now the nodal coordinates are the general kinds that we use the most, and actually there are a number of sub-cases in that category. We'll start by thinking in general. The nodal coordinate system is used to identify where the nodes are located, and then secondly, when you're at that node, to orient your displacements, constraints, and other quantities at that point. The given node can have 6 degrees of freedom, and this is typically the default situation in general purpose finite element codes, because they expect that you will have a mixture of structural elements and elasticity elements that will use both the rotations and translations. There are many notations used to characterize those 6 degrees of freedom. You can use symbols such as shown here with the subscripts and distinguishing between translational and rotational. Here you have just the numbers, and this is universal, 1, 2, 3, 4, 5, 6. Everyone uses these numbers at times to define the translations in the x, y, and z directions, and then the rotations about the x, y, and z axes. Thirdly, people often will use the symbols T and R for translation and rotation, and that's somewhat similar to our first case above. And lastly, below, you might give the node numbering as a part of this description. Use the symbol either U or theta to define if it's a rotation or translation, and then give the axis, the x, y, and z, to tell about which axis you are defining your quantity. Now the sub-cases under the nodal coordinate system are going to be discussed next. We've already mentioned the basic system. Someone might call this the underlying coordinate system, and some people might even call it the global coordinate system. I'll use the term basic coordinate system in this course. That's the default system, and it's the right-handed Cartesian system shown below. Now, in addition to that, a person might define some local coordinate systems. These could be any one of the Cartesian, cylindrical, or spherical types, and you might use those then to tell what's going on out here at some part of your structure. I'm showing a local rectangular coordinate system here. For completeness, I'm going to mention a kind of coordinate system used in the Nastran series, and that's called the global system. You might think of it as the solution set of coordinates. It's defined as a union of all the local coordinates in your system. So for instance, around a hole here, the user might have defined a cylindrical system, and I show those degrees of freedom in green here. Other parts of the body might have used systems that are basically the basic coordinate system and would be in those directions. Then I formed a vector on the right to show that if you refer your coordinates then to the appropriate local system, your degrees of freedom 1 and 2 here are going to be inclined in these two directions. Your degrees of freedom 3 and 4 are going to be inclined in these directions, and you notice there's some sign differences. And then 5 and 6 are going to be inclined at these oblique angles. Now they're all orthogonal coordinate systems, so they're always perpendicular to each other at a given point. Now, this might be the optimum system in which to solve the problem, because, for instance, if there were a rigid, slippery shaft in here, you might want to put a boundary condition that there's no radial displacement allowed in these radial directions, but that there's no force in the tangential direction. And so you can see how such a local system might help clean up the boundary conditions. If you don't do that, the alternative would be then to have what's called a multi-point constraint at each point, and that would involve some work in setting up the equations, but is also possible. The second major category of coordinate systems deals with the element coordinate systems. And here I show three different kinds of elements, each of which has a preferred coordinate system. This element coordinate system would be used by the developer of the element primarily, but often is important in interpreting the data or the results that come from the solution. Here's a beam element or a rod element that requires an axial coordinate and then a couple of lateral coordinates. Here's a plate-like element that would have a two-dimensional system, still orthogonal but specific to that particular element. And lastly, solid bodies often have curvilinear coordinates. A third major category of coordinate systems is that dealing with material coordinates. There are many materials now that are orthotropic. We have many laminates and other exotic materials. Given a typical element such as the quad element shown here, a person might want to rotate a coordinate system such as this material coordinate system shown from some known reference. Now in the Nastran series for their quad plate element, the reference is the side that has been created with the first two node numbers in the connectivity card. And then the angle of rotation shown is actually theta, and so that will give you an element-specific material coordinate. Now, if you don't specify in this particular element a material coordinate system, then you get the one with theta 0 by default. And that's not obvious, you see. Every computer program will probably do this differently because this does not default to the element coordinate system, but rather to this coordinate system aligned with one side of the element, and that's not the element system. Now let's start thinking about the mathematics of the two-dimensional coordinate transformation. By this I mean that primarily we'll look at rotations of two orthogonal coordinate systems at a point. Now you also can consider translations, but translations usually don't affect the stiffness matrix in the same way that a rotation would. The general motivation for what we're about to do is maybe given in this straw man experiment here. It's kind of a mental experiment. What if we tried to directly assemble stiffnesses of two bodies that are inclined as shown? Now these would be bodies that would have their own elemental coordinate systems which are axially aligned. And so when you got to the common node and tried to overlap it, you would have these different displacement and force components to be added. Now, you can't add those directly. You've got to somehow decompose those and put them all in terms of some common unifying coordinate system. So you can see that we need that approach at a point. Now that will probably mean rotating one or both of those sets of forces and displacements. Before starting on our mathematics, I'd like to mention some small points. First of all, the notation that I use using these curly braces and square brackets and so on to represent vectors and matrices really does one bad thing, and that is that it suppresses the base vectors that are used. So when we give matrices that have numerical entries, the user in his mind must understand what coordinate system those numbers refer to. And of course, in contrast, many people in physics and fluid mechanics will use the notation shown here, where you'll carry both the component involved and the base vector. Now, that's a lot of baggage to carry on, and up until this point it hasn't been very important because we've presumed a single underlying coordinate system, so the user typically wasn't confused about which coordinate system was being used. That notation, by the way, was of the curly braces and square brackets and so on, was developed by Fraser, Duncan, and Collar in England in the 30s, and I think primarily in the fluid mechanics and aeroelasticity area. Now, I mentioned earlier about translations and rotations, and these are not the same kind of operation, because a translation of base vectors doesn't really change much in the stiffness matrix or in the physics of the problem. On the other hand, if you rotate the base vectors, then you really do tangle the degrees of freedom in any orthogonal coordinate system. So the fact that translations are relatively placid and rotations are relatively dangerous is really fundamental, and you must keep that in mind. It's one reason that we were able to make simple assemblies and solve them directly after finding element matrices, because we weren't bothered by the translation of the element coordinates to the underlying coordinate system in which we solved the problem. Now let's set up the equations for the key transformation that we can study, which is a rotation in 2 dimensions. The basic physical item here is this red vector, and that's a physical quantity that we're going to refer to each of 2 coordinate systems, and then figure out how the components in those 2 coordinate systems are related. Now you can see that I have already shown the components. If you project to this global coordinate system, and what we'll do is set up the projection onto the element coordinate system. Now, one way to do that is to do it stepwise, and now to decompose the global components into the elemental components. So that's what I've done below. If we do that, we see that there's a component U1 global shown here, and it's going to contribute to the U1 in the element coordinate by projecting to that coordinate axis through this angle alpha. So alpha there being an acute angle means that we want the cosine of alpha for that projection. Then we would like to superpose on that one the component of this U2 global that will help, and that will be the U2 global times the sine of the angle alpha. When we get done with that decomposition, now let's work on the component along the y element axis that we'll call U2 element, and we will project back from this green U1 vector, and this time it's for a positive alpha, we're picking up a negative contribution, so that's where that minus sign comes from. And then lastly, we'll project the U2 onto this axis, and that will be a U2 cosine alpha. Now this matrix has a particularly nice form, it will turn out, and we'll show that in the next figure. The coefficients of the transformation, when assembled in matrix form, make what is called an orthogonal matrix. This has several interesting features, including the fact that the determinant of the matrix is unity, because it's cosine squared alpha plus sine squared alpha. And what we've got now is a matrix with small t for transformation that can convert the components of a vector in global coordinates over to a set of components referred to the element coordinate system. Now, you can do this rotational transformation node by node, and it might not be that it would be the same angle at each node. So I'm allowing for the fact that there might be an alpha at node A that's different than alpha at node B, and so on. But by assembling the transformations at each node into this larger matrix, you get this kind of a banded form. There's no interaction between the nodes in terms of this transformation, so it's largely zeros. Let's denote the assembled set of transformation matrices with a capital T, so we can write our expression shown here. Now this capital T itself is orthogonal, and the major point about orthogonality is that you have the inverse matrix equal to the transpose of the matrix. That's very useful because the transpose is relatively easy to do, whereas the inverse is more difficult operation. And then I repeat the idea that the determinant of such a matrix should be unity. And that's true for the total transformation matrix as well as the matrix just at a single point. Now, we've been talking about a general vector. I have emphasized the displacement-like character because of the use of the symbol U, but that same logic goes through for the force vectors. They both are physical vectors with similar components, and they both transform the same way. So we know how to transform forces and displacements now, but we haven't yet learned how to transform the stiffness matrix. That can be done by looking at the equation of equilibrium here, and we know how to transform the two vectors that are involved, but not the matrix. So we do that, and we'll do it in the direction of going from the element coordinates into the global coordinates shown below. We do that on both sides, and then because the transformation matrix T is a relatively placid matrix, we can invert it, and furthermore it's orthogonal, so we can set the inverted form equal to the transposed form of the matrix. Now, if we lump together the three matrices shown with the curly brace, we find that those terms play the role of a stiffness because they relate a displacement on the right to a force on the left. And that we consider now to be our global stiffness. This transformation happens to be in the proper direction for common use because you usually do start out with an element stiffness matrix. That's where it's easy to derive it, and then you would convert it into the global version that you would need for assembly and solution through this transformation. Let's do a numerical example showing the transformation of a stiffness matrix. We'll use a planar truss as our case, and the element under consideration is the red one, which is a truss member inclined at 30 degrees as shown below. Our job will be to find the element stiffness matrix in element coordinates embedded in 2 dimensions, and then to convert it to a stiffness matrix referred to a set of global coordinates. First, we must take the stiffness matrix for a truss member, which we called a rod earlier, and embed it in 2 dimensions. Then we'll carry out our transformation. Here's the 2-dimensional embedding of that stiffness. We have the common EA over L terms, which is the stiffness on axis of such a member, and then the zeros show that there's no coupling with other coordinate directions. So basically this is a rather specialized element that only has on-axis stiffness and no lateral stiffness. The transformation matrix that we're considering would be composed of the transformations at the two ends of the truss, and there's a 30-degree coordinate transformation at both ends. For us, it will be a plus 30 degrees going from the global to the element coordinate axes. I put those numbers in, and you see the cosine of 30 degrees and the sine of 30 degrees, and these are sprinkled about in the matrix. We now have the ingredients for calculating the stiffness matrix in global coordinates. We have found the transformation matrix. We can take its transpose and multiply by that element stiffness matrix where we had embedded the truss element in 2 dimensions. And I won't show those detailed calculations. As you can imagine, they come out as shown with a lot of squares of the trigonometric functions. Then if you put in the specific angle that we're interested in, which was 30 degrees, you get this set of numbers as the global stiffness matrix for that inclined element, but referred to the coordinate system that is oriented horizontally and vertically. I'd like to check the validity of that stiffness matrix by looking at a couple of physical examples. For instance, if we were to move the left node horizontally 1 unit, then the quantity K11 would be the horizontal force generated by that displacement. Now, that's pretty much on axis, and we'd expect that to be larger, and it is 0.75, than a corresponding vertical displacement, which would be more off axis. Now, the vertical displacement will give rise to a stiffness K22, which would be the vertical force in degree of freedom 2 due to that unit displacement. And that number comes out to be 0.25, which is only 1/3 as much. So this certainly checks our intuition. Now, at the conclusion of a run, after you have a global solution to the problem, you might want to recover element results, and then that would require the mapping back into element coordinates and transferring displacements in particular back to the element. So that's easily done. You've had a pretty good look at 2-dimensional rotational transformations. Let's consider 3-dimensional rotations for a moment. Such a 3-dimensional rotation is sketched at the bottom here, where you have a reference coordinate system, perhaps a global system, and then out here a different one, perhaps an element coordinate system. Now, this is really a difficult topic to transform the coordinates of vectors and other quantities through 3-dimensional rotations. One reason is that the angle changes don't commute in 3D, so that you have to do things in a very prescribed, careful order. You can have singular directions, such as found in flight mechanics, where one is perpetually comparing such a coordinate system on the right, which might be attached to a vehicle, with some earthbound coordinate system on the left. I regard this as an advanced topic, and indeed the textbooks in the field of finite elements usually don't even comment on this. Well, it's time for a problem session. I'm going to do 3 example problems, and they're going to involve trusses and beams. Problem 1 is the deflection of a derrick. So here I have a boom-like body that will carry a live load at its tip. We'll actually make this boom out of 2 trusses in the form shown, one truss at 45 degrees, the other at 30 degrees. The question is to find the elastic deflection at the tip of the boom due to that 10,000 Newton load. We're given the characteristic of each of those truss members. The solution to this problem involves the assembly of two trusses. Now there are going to be 4 degrees of freedom that will be fixed at the base, and then there will be 2 degrees of freedom at a common node at the tip of the derrick that will be our independent degrees of freedom. Here's a sketch of the finite element mesh, and we're numbering such that the first element going from ground to tip is inclined here at 30 degrees. We know how to write the stiffness matrix for that element in its element coordinates, and then we've learned how to write the stiffness matrix in the global coordinates. Now I'm showing that below here in a coordinate system that's aligned with the horizontal and vertical directions. I'm putting dots where I don't care about the entries, and we can see the dominant terms that we're going to need at the 5 and 6 coordinate directions. The second element contributes a stiffness matrix in a similar way, and we're only interested in those connectivities to degrees of freedom 5 and 6. Of course, the angle involved is different, and so the terms are a little different. Then we can sum these two stiffnesses together by embedding them both in an expanded 6 by 6 matrix. We know that the degrees of freedom at the base are going to be constrained. We know that there's a vertical 10,000 Newton load downward at the tip, and we know that there's no horizontal force. So that gives us a set of 2 equations and 2 unknowns. I'll show those 2 equations that can be partitioned out from the other 4 equations, and here they are. Now we can solve this by simple elimination of variables, such as you've learned many years ago in high school, or you can use Cramer's rule, and I'll use Cramer's rule since it's a simple problem. And in so doing, you get 0.241 millimeters as the horizontal displacement and minus 0.308 millimeters as the vertical. I sketched that down below, and this shows that, as you would expect, the truss system has translated a bit to the right and then quite a bit downwards under that downward load. Problem 2 considers the stiffness of an Euler Bernoulli beam and how it transforms under a rotation of the coordinate system. We will consider an Euler Bernoulli beam in flexure in the xy plane. We aren't interested in the axial stiffness of the beam nor axial loading, but we do have to have the degrees of freedom involved to consider lateral bending in either of the coordinate systems. Now, if we do that, then we have to carry both the vertical and horizontal components of displacement in this xy coordinate system. In the element system, this is our given stiffness matrix, where we're considering the degrees of freedom in the element axial, the element lateral, and the rotation about the z-axis at each of the nodes. So we end up with the 6 by 6 stiffness matrix. The problem statement asks for 2 things. First, we're asked to develop the nodal coordinate transformation matrix, little t, that relates our element coordinate system to the basic or underlying system shown. The basic system in our example will align with the horizontal and vertical. Then we're to identify the stiffness term K11 that is in the basic coordinate system. So, in other words, for our inclined beam, we're asked to relate quantities to a more universal system that is aligned horizontally and vertically. Well, we already know how to do the part where the coordinates rotate and the translational degrees of freedom have to be interpreted. So we've already done that. We had possibly these translational degrees of freedom, and then they might be rotated to some new coordinate system. And that goes straightforwardly, and that actually will allow us to find the T matrix, which I'm boxing here. But the other thing would be, what about this rotation that we might call degree of freedom 6? Is that affected by a rotation of the coordinate system about its own same axis? And the answer is no. That rotations about the z-axis are the same in the initial element coordinate system as they are about the basic coordinate system. And so I show basically an identity here, and you don't get any change in the rotational quantities. So this answers the first part to our two-part question. Now for the second part, we can find the basic coordinate system by forming the system transformation matrix, which involves two of the above nodal transformation matrices. We'll form our transformation matrix for the system by taking the two matrices for the two nodes. Then we'll transpose that entire system matrix and show it here. We need to form the terms in this matrix triple product in order to calculate the stiffness matrix K, and I'd prefer to do that in index form. The free indices I and J occur in interior in locations here and here. When we go to our specific case for K11, therefore, we put a 1 in this location and a 1 in this location. The sums initially should be over 6 terms, rows or columns, but we soon see that this transformation matrix T, whether you take Tm1 or Tn1, you're talking about terms along this row, and those that are above m or n greater than 2 are going to vanish. So I need only consider the sum up to m or n equals 2. And finally, if you look at the stiffness matrix written 2 figures earlier, you'll find that when the indices m and n range only over 1 and 2, there's only one non-zero term, namely K22.